Welcome to the course on computer design of electrical machines. We will have a lecture 13 today, design of three-phase induction machine, the part 2. Well, in this we would like to cover today magnetic circuit in electrical induction machine especially. So coming to typically to as a just like as a kind of review, the path of the magnetic flux is called magnetic circuit. To calculate the parameters such as inductance from the physical dimensions, we need an understanding of the electromagnetic behavior of the machine. A review of the magnetic circuitry laws applied to electrical machines is now explained. So where we can call it like we have to define different parameters. Phi as a magnetic flux in Weber, A is the cross section area of the magnetic path in meter square, L is the length of magnetic path in meter, and B is the flux density in Weber per meter square or Tesla, and H is the ampere turn magnetizing force in ampere turn, normally denoted in ampere per meter, and AT is the total MMF in typically again in ampere terms. So now the other parameters are mu, that is equal to mu r into mu 0, that is multiplication of absolute permeability. You can call it the relative permeability multiplied the permeability of the space, and mu 0 is the permeability of the space, that is 4 pi into 10 power minus 7 Henry per meter, and mu r is the relative permeability and its dimensional parameter, and S or R is the reluctance in ampere Weber, and rho or P is the permeance in Weber per ampere. Now coming to typically for the calculation, we have studied that analogous to electric circuit, the magnetic circuit also shows the following behavior, that the flux is equivalent to the current of electric circuit. Here we call it flux, that total ampere turns divided by the typically the reluctance. So or it is 8 into the rho, that's a permeance, and so from this we can call it the reluctance, that's length upon area into 1 upon permeability, that's called L upon mu A, is really the typically called reluctance. So where H is 80 mm per unit length, and that is equal to flux into reluctance upon unit length, because this length is taken out from the both the relation. So it's, you can call it per unit length like or per meter like. Now coming to typically H, that is a small at flux into reluctance per unit length. So for the case of material of length H carrying the uniform flux, the total MMF will be H equal to H into L, and that is small at into L. So that we can call it H equal to phi to 1 upon L into typically L upon mu A. So it becomes phi upon A into 1 upon mu, that is B upon mu. So in series magnetic circuit, the total reluctance of is the sum of the reluctances of individual parts. So that's S equal to S1 plus S2 plus S3 plus S4 plus all the further reluctances of magnetic path, like where the flux is flowing. Now we can come the total MF acting around the complete magnetic circuit, AT is equal to phi S, where the is phi and multiplication in bracket S1 S2 plus S3 S4, and AT is again 81 82 83 plus 84, and or it can be written small 81 into L1 or plus 82 L2 plus 82 L3 84 L4, considering that the different parts of magnetic circuit have a different reluctances, and that's why they have a different MF consumed, and total you can call it AT can be also taken as a line integral of small at into the length like. So considering of course here, because we are using a typically the different materials in the magnetic circuit, typically the ferromagnetic material. So here we can see the magnetization BH curve or B versus AT curve of ferromagnetic material, showing the saturation in the characteristic. If you see, they are reasonably non-linear except leaving the initial portion. So these characteristics denotes given for one notation is for sheet steel, then second is steel, third is cast steel, and fourth is tungsten steel, fifth is the magnet steel, and sixth is cast iron, and seven is nickel, eighth is cobalt, and ninth is your typically the magnetite. So these are the characteristic, you can call it BH characteristic of different ferromagnetic material at different, you can call it like a typically which they show the behavior, and we have to consider these characteristics when these, you can call it the material are involved in path of magnetic circuit. You can call it in parallel circuit, that was series circuit. In parallel circuit, the same MF is applied to each of parallel path, similar to that same voltage applied for in electric circuit, and the total flux divides between the path in inverse proportional to their reluctance, as corresponding to that. As in electric parallel circuit, you can say the total current is the sum of all the currents of different parallel paths. So here also the net flux is sum of all the flux for different parallel paths. So you can call it phi equal to phi1 plus phi2 plus phi3 divided by typically 80, or you can call phi divided by 80 will be phi1 upon 80 plus phi2 80 plus phi3 by 80. So, or you can call it 1 upon s equal to 1 upon s1 plus 1 upon s2 or 1 plus s3, or equal to, or you can call it permeance rho equal to rho 1 plus rho 2 plus rho 3. These are the permeance of different parts of magnetic circuit, parallel circuit. So now coming to the typically a magnetic leakage, I mean, because normally you can call it flux really confined to path of a ferromagnetic material, but in some cases, I mean, you can call it the flux, I mean, really go to not only confined to only ferromagnetic path, but some of the path, some magnetic flux certainly have a, you can call it a small path or a leakage. So that we call it, it does not typically link to the entire magnetic circuit, so it's confined only locally, so we call it the leakage flux. So it is impossible to confine all the magnetic flux to given path, and designer job to provide path for low reluctance to reduce the leakage of the flux. And why it is more leakage flux? Typically, you can call it the more MF required and current returns and needed to compensate for the leakage flux, which, however, it does not contribute to the for energy conversion or the requirement of these typically machines like. So leakage flux does not contribute either to transfer of conversion of energy, however, the leakage flux affects the performance of these rotating machines like. So for coming typically for magnetic circuit calculation, the term leakage coefficient is defined, that is CL equal to useful flux plus leakage flux divided by total useful flux. This is called a leakage coefficient, and that is equal to total flux upon useful flux. So this is normally, you can call it more than one like. Well, we can have a calculation of total MF in magnetic circuit, and normally in magnetic circuit in rotating machine, certainly we have the air gap. I mean, normally it considered depends on the magnetic path. Normally we have a two air gap in a one total path which passes from stator to rotor from one side and then come back to another side. So you have a two air gap for this. So we usually, I mean, there is a method to calculate the MF required for air gap, because the major amount of MF is consumed by the air gap. Ferromagnetic material, because of high permeability, require very less MMF. Like, I mean, of course, that also we cannot neglect. But what I mean here that I mean, typically calculation of MF required for air gap becomes very important, but it's contribute around more than 90% requirement of MF of the machine like. So coming to for the calculation of MF for air gap, we define the different dimensions. L is the length of core, small lg is length of air gap, and ys is the slot pitch, ws is the width of the slot, wt is the width of the teeth, and wo is the slot opening, and n is the number of radial ducts, and w is the width of the radial duct. So reluctance of air gap, that is typically a one slot pitch, that is you can call it Sg equal to 1 upon L upon mu 0 A or equal to Lg upon mu 0 L ys like. So now you can call it in the slotted armature, the effective area of the flux path is substantially decreased, resulting in increase in reluctance of the air gap. So you can just see here how typically the means slot and air gap are involved in this geometry. I mean, unslotted structure and slotted structure. Unslotted structure means you are using typically a totally closed slots, and on the air gap we don't have a typically presence of the slot. But in slotted structure we have certainly, I mean, the slots are up to the air gap, and that's why we have a teeth, and most of the flux concentration, or you can call it through the only teeth, a very small flux flow goes through the slots, like where the you can call it winding is placed like. So effective or you can call it contracted slot pitch equal to ys dash equal to your wt into ynus minus ws. So reluctance of slotted armature will be S, typically G will be Lg upon mu 0 ys dash Ls, and that is equal to Lg upon mu 0 L in bracket ys minus ws. I mean, because of the, you can call it presence of the slot also, I mean, responsible for, I mean, typically reducing the, I mean, path of the width of the slot, means major flux typically flow through the environment typically only through this path only. So coming to that, however, there is a fringing or the flux present, so reluctance more than smooth, but less than earlier slot assumption. So flux over one slot pitch is distributed over W2 plus delta sigma s Ws, sigma Ws. So effective slot pitch will be Ys dash equal to W2 plus sigma Ws, and that will be Ws plus Wt plus Ws plus sigma Ws minus Ws. So it comes minus Ys minus 1s 1 minus sigma equal to Ws, or equal to Ys minus Kcs into Ws, where Kcs we define it typically a kind of Carter coefficient or Carter gap coefficient we talk about. So Ys is equal to Ys minus Kcs into Ws, and depends on the ratio of the slot width to gap length. And empirical formulation for KCS is KCS equal to 1 upon 1 plus 5G divided by Ws, and calculation coefficient for the parallel sided slot. Of course, for different type of slots, these are different formula. KCS equal to 2 upon pi in bracket tan inverse y minus 1 upon pi log under root 1 plus y square, by close with where the y equal to Ws upon 2Lg. So now you can just see how the Carter gap coefficient varies with the slot opening to gap width. And here you can, for the calculation of this, so you can call it the Ks is higher for the semi-closed slot than open slot, and lower the ratio on the y-axis. The closure is the actual slot pitch to the design for slot pitch. So you can just see as the slot opening for gap length, as it is increasing, you just can look into it typically for both kind of the slot, how the Carter coefficient changes like. Well, reluctance of air gap with slotted armature, we can say Sg equal to Lg upon mu 0 ys dash into L, or Lg upon mu 0 L in bracket ys minus Kcs Ws, and let's ratio of the reluctance of air gap of slotted duct be Kgs. So Kgs will be equal to ys upon ys minus Kcs into Ws. So this Kgs gap contraction factor for slot, and the reluctance of air gap with slotted armature is Kgs times that of the smooth armature, and Kgs has the value greater than unity. So now coming to this typically, for again calculation this MF for air gap, the provision of radial duct, we also have a for larger machine provision of radial duct, so that's also affected. So effective air gap length of the machine is reduced owing to the presence of duct and increased reluctance of the air gap. So effective axial length will be L dash equal to L minus KCD into NDWD, where KC is Carter coefficient for duct and usually Carter coefficient versus opening oblique with chart of the cases, as you can see in the typically here for the duct, also ventilating ducts also in the typically in the stator core. So now coming to the typically here the ratio of the reluctance of air gap with duct to reluctance of air gap without duct to be KGD. So that will be L upon L minus KCD and DWD into KGD, and that's a typically gas cup gap contraction factor for duct. The effect of both slotting and ventilating duct can be allowed for in a single expression. So we can call it reluctance of air gap of a smooth armature without duct will be Lg upon mu 0 L into Ys, and reluctance of air gap with the slotted armature with duct will be L dash Lg upon mu 0 L dash Ys dash. So L dash is responsible for duct and Ys is responsible for slotted structure. We can call it the ratio of this reluctance of slotted armature with ducts and related armature without duct will be Kg equal to Ys upon Ys dash into L upon L dash, and that will be Ys upon Ys minus Kcs into Ws into L upon L minus Kcd into Ld Wt. So that becomes typically Kgs into Kgd, the multiplication of both the coefficient, one the coefficient because of the, you can call contraction of coefficient because of the, you can call it like a because of the ducts, and another because of the slotted structure. So we can call it for this MF, we can call what is Kg, Y is upon Ys dash into L upon Ls dash, and that becomes typically what we already discussed, Kgs into Kgd. So Kg is the ratio of reluctance of air gap of a smooth armature without duct, and it's called total gap contraction factor for slots and duct. And for induction motors, the slots on both stator and rotor, it is important to calculate the gap contraction factor for stator and rotor. So we have here the KGSS means gap contraction factor for stator slot, KGSR gap contraction factor for rotor slot, and KGS is total gap contraction factor for slot, that is KGSR into KGSS. So you have to consider the contraction factor for due to stator slot as well as for rotor slot. And then coming to gap contraction factor signify the reduction in the effective slot pitch, therefore the change in the reluctance. However, it will make more sense if this was translated to the air gap length. So from the gap contraction factor, the MF required for the gap with slotted armature is kg times the MF required for gap with the smooth armature. So that becomes the kg equal to ys upon ys minus kcs into W. O. So now coming to calculation of total MF in magnetic circuit. So you have in magnetic circuit, of course, the air gap and other part. So considering first as a typically MF for the air gap, it is typically 8 into 10 to the power 5 into B, where the B is the absolute flux density in the air gap. So we can call it MF per meter for air gap length. With the smooth armature will be ATG equal to MF upon meter in length, and that is 8 into 800,000 into B into LG, and MF per meter for air gap LG with the slotted armature will be AG upon MF per meter into length, that's a 800,000 into kg into BGLG, and then ATG will be at 800,000 kg pi upon AG into LG, and that becomes 800,000 phi upon AG upon kg into LG, and it becomes 800,000 phi upon AG dash into LG, where AG dash is AG upon kg, and area has a typically contraction factor into account. Now coming to typically the area of the gap per pole will be AG is equal to slot per pole into slot pitch into pole length, and that is AG equal to S upon P into YS into L, and you can call it that will be AG dash will be AG upon kg, that is S upon P into YS into L, divided by L YS divided by L dash YS, so it becomes equal to S upon P by dash YS dash into L dash. So MF required for the smooth armature is ATG, it's 800,000 to BGLG. MF required for slotted armature is ATG equal to 800,000 to kg BGLG, and that becomes virtually 8,000 B into kg-LG, where the air gap increase from Ig to kg-LG. Your kg is always greater than 1. So it means say effective air gap length increases because of the slotting or these factors of ducts like So that's the total MF required for the air gap. Now coming to the calculation of remaining part of the magnetic circuit, so we can say net length of the iron, gross iron length is LS. Thus LS is the slot portion of conductor. So core that equal to core length minus length of ventilating duct. So that becomes L minus ND into WD. So net iron length Li is equal to Ki into L minus ND WD, and where the Ki is the stacking factor of the steel lamination, as you can see here like Now coming to MF for teeth, the calculation of MF necessary to maintain the flux in the teeth is difficult owing to the following complex problems. The complex shapes of teeth, that is tapered, wedge tapered, parallel. The area presented to the flux is not constant throughout the teeth, throughout the tooth height. So we can call it the slot parallel path for the flux, and always some leakage present. So these three methods of determining the MF for teeth. So first is the graphical method, the another is the Simpson method, Simpson rule, and third is the BT 1/3 method. So coming to here, typically for the MF calculation by these three methods for the MF for teeth. So you can call it first for tapered teeth. So total MF required for tooth is ATT, that is a mean ordinate as it is shown here, into height of the teeth, and that comes ATT equal to AT mean into L teeth. Now coming to the typically other method, 3 ordinate Simpson rule, that is AT mean equal to 81 plus 482 plus 83 divided by 6, that is shown what is the 81 and 82 and 83 in typically in the distance from the root of the teeth like and how it is the total TS equal to DS. So simple teeth, that is uniform taper, that is assumption AT varies at parabolic. So AT typically calculated for 3 equal distance point, like we can call it the third method is BT 1/3 method, that is BT 1/3 method, flux density is 1/3 height of the narrow end of the teeth, and 83 will be value of the MF per meter for BT 1/3. So total MF for teeth will be 80 capital 80 into T, that is 80 1/3 into LT, and assumption the value of 80 obtained from flux density at the section of 1/3 of the teeth height from the narrow end, and is the mean of 80 for the whole of the teeth. So simple method provides sufficient accurate results like. So coming to typically effect of leakage flux, it is impossible to confine all the flux into the magnetic circuit. As we already discussed, there is always a leakage. The alternate leakage flux induces voltage in the winding to which it is linked. That is leakage reactance voltage, and this reactance play an important role in the AC machine. So estimation of leakage flux is difficult due to complex geometry path of the leakage path. So leakage flux can be assumed to consist of flux tube of length y and a constant width delta x, along with the effective depth of the length of the typically of the field, as you can see in the typically here in the diagram that you have a dimension typically how it is going to be really affecting the leakage flux of the two sides of the typically of the ferromagnetic material. So tube permeance delta sigma will be equal to mu 0 area of the tube into length of the tube, and that is equal to mu 0 L into delta sigma, that we consider the delta x divided by y, and permeance of whole field we that is rho equal to mu 0 integral L dx upon y, that becomes equal to L mu 0 into integral dx upon y. So you get a specific permeance your lambda equal to your rho upon L, that is mu 0 typically integral dx upon y. So it comes as a specific permeance per meter unit length. Like, well, we have a leakage reactance when the leakage flux is associated with the winding carrying the steady state AC, a reactance voltage is produced, and the magnetic reluctance offered to leakage flux is predominantly due to the air gap path under normal condition, and so leakage reactance is directly proportional to the current, giving a constant inductance. Therefore, the reactance voltage may be regarded as due to the voltage drop in the constant leakage reactance. So this leakage reactance we can define as coil with the T turns with current Iz, effective permeance of flux path rho, that is the inductance defined as a flux linkage per unit current. So inductance define flux linkages of winding upon the current, and that becomes T phi upon Iz, or where the phi is equal to MF into permeance, that is T into Iz into rho. So inductance becomes T square Iz upon rho divided by Iz, that becomes T square rho, that's a T square into permeance. Like, well, so you can call it like this inductance can be also defined, that is this is T square rho, or if the current pulsates with the frequency f, so we can call it reactance equal to 2 pi f into inductance, that becomes 2 pi f into T square rho, and where the x is equal to pi f T square rho or 2 pi f T square L into lambda, where lambda is equal to mu 0 integral of T x upon T square into dx upon dy, where Tx is the number of the link turn and lambda is the specific permeance for the leakage path. So this you can call it the leakage reactance. So x is 2 pi f T square into rho or 2 pi T lambda. So where the rho is your pi mu 0 into integral of T x square upon x dx upon I. So lambda difficult to estimate. So magnetic circuit is broken into sets of series and parallel path, and specific permeances of each path is calculated. As you can see, rho is equal to mu 0 as a resultant permeance, and that comes A1 upon L1 plus A2 L2 plus A3 L3, or equal to mu 0 in bracket L1 into W1 upon L1 plus L2 into W2 L2 plus L3 W3 L3 plus other parts, and that becomes rho equal to permeance equal to L1 lambda 1 plus L2 lambda 2 plus L3 lambda 3 plus four other parts. Like, so you can call it the, that is about the total, you can call it the leakage. And now calculation of magnetizing current. So total M required to be provided by the exciting winding is the sum of the MF for several series path of magnetic circuit. The value of exciting or magnetizing current depends upon the total MF required, the number of turns in exciting winding, and upon the way in which the winding is distributed. So magnetizing current for concentrated winding comes in concentrated winding. It is assumed that the whole flux links with the turns, and magnetizing current is Im equal to AT upon T, and RMS value of magnetizing current Im equal to Im maximum upon kph, and that is kph is a peak factor, and since the current wave is not sinusoidal, so kph differs from square root 2. So coming to typically this magnetizing current for distributed winding, so we can call it the sinusoidal, for the sinusoidal flux distribution. If the flux is steady and is sinusoidally distributed in space, the value of magnetizing current is Im equal to MF for peak flux density divided by winding turns, so it becomes like ATM upon T. So a three-phase winding is uniformly distributed in space with 60-degree phase spread and excited with balanced sine wave current, give the amplitude of fundamental of magnetizing current AMT equal to 2.7 Im TPH KW1 divided by P, where Im is the magnetizing current per phase and TPH is turns per phase. You can call it like this. ATM1 is 2.7 Im TPH into KW1 upon P, and the value of magnetizing current per phase is Im equal to 0.37 into P ATM1 divided by K TPHK omega 1 like. So now coming to typically this magnetizing current calculation for distributed winding. So typically considering the non-sinusoidal flux distribution. So due to saturation, MF wave becomes flat top instead of sinusoidal, which can present as you can see in the figure how the flat top is the waveform given here typically for the flux. So this flux density becomes like P0 equal to Bm1 sin theta plus Bm3 sin 3 theta plus Bm5 in sin theta. Because it's symmetric about x-axis, the only odd arm will be there, and because of flat top, we can just say typically third typically is out of the phase. So we can call it B0 is the flux density at angle theta from the neutral axis, and Bm1, Bm3, Bm4 are the fundamental and the harmonic of B, that is first and third only, if you consider first and third only here, like maybe. So now coming to typically for, of course, this magnetizing current for non-reflective, suppose we consider the 2 points which are displaced 60 degree from interpolar axis, the flux density at 60 degree, typically theta equal to 60, it comes this 60, that is Bm1 sin 60 plus Bm3 sin in bracket 3 into 60, so it becomes B60 equal to Bm1 under root 3 by 2, so it becomes Bm1 pi by 2 into B average 1, and B60 becomes root 3 by 2 into pi by 2 into B average 1 equal to 1.36 B average. So this we take into account, like, so we call it the calculation for the remainder of the magnetic circuit which is affected by the central flux distribution can be worked out as follows. The MF acting at theta equal to 60 degree, we call it AT60, that's ATM sin 60, that's root 3 by 2 into ATM, that becomes root 3 by 2 into 2.7 IPS TPH KW1 divided by P, and then IPS becomes 0.427 A P into 8060 divided by KW1 into 2PS. So that comes the typically the magnetizing current line. Now coming to estimation of operating characteristic, this is virtually how we can find out the operating characteristic starting from design specification of electrical and magnetic loading, obtain the main dimensions as for the design we talk about already, the adjustment of the construction and geometry data, and verification of electric and magnetic loading, and computation of magnetizing current, then computation of equivalent circuit parameter, computation of loss and slip and efficiency, and computation of power factor, starting current, the torque and temperature rise, and to check is the performance satisfactory. If it is not, then we have to go again in the iterative manner, or if yes, then we close the design. So now coming to the steps for this main steps for induction motor design here. Step completes for the design of starts with the design specification and the assigned value of flux density and current density B and J are used. Physical dimension of the machine such as stator sizing, inner and outer diameter, stack length, stator slot sizing, wire gauge, etc., and rotor sizing, inner and outer diameter, stack length, and rotor slot sizing and ending dimension, and area is done. And the deduced value are then adjusted to closest standard value. So now the actual magnetic and current loadings are verified. A loop for verifying the teeth saturation factor can also be added here, and then the magnetizing current is calculated in step 4. The equivalent circuit parameter are obtained in step 6, and losses, rated slip, and efficiency are determined in next step. So finally, power factor, log rotor current, torque and breakdown torque, and temperature rise are also assessed. So coming to this operating characteristic, first magnetic circuit calculation. So coming to magnetics, in all electrical machine, the magnetic circuit is the main medium for energy transfer from one form to another. An induction motor, the alternating flux is required to be produced for torque development in minimum space and with minimum iron losses, and the MF required to produce the given value of flux density, and the resulting watt loss, iron loss in different machine parts must be considered. So these are assessed utilizing the magnetization characteristic and loss curve. So now coming to here, the different parts of machines cross section taken into consideration while calculating the loss as a part of magnetic circuit. We have 5 parts of magnetic circuit like stator core, stator teeth, air gap, rotor teeth, rotor core. So here you can see how the motor cross section is showing the different parts of magnetic circuit with the different the flux distribution as well as the flux density here. You can call it, we can start from stator core, then go to stator teeth, then air gap, rotor teeth, and rotor core. So the magnetization best watt loss curve are given here for a material, which we are using the material in the ferromagnetic material in the path of this. So this is first magnetization BH curve given for the material, and the second characteristic is of course the frequency sensitive, which is given the your flux density in Tesla to the watt loss per kg for the ferromagnetic material at different frequencies, like because we expect that maybe the machine will be operating at different frequencies. So these are characteristic for different frequencies, like, but at of course at 50 Hz this loss is quite low, like. So for the calculation of magnetization core loss curves, the calculation of MF required for the certain magnetic part done, find out the flux density in that part. So corresponding to that flux density, the ampere conductors per meter are found out from the magnetization characteristic in shown in next slide. The value of the ampere conductor per meter ATM are multiplied by the length of magnetic path in various part of the magnetic circuit to get the total ampere turn in that part MF in that part of the machine. So coming to here, typically for various parts in DC machine, the flux is assumed to be uniform over the cross section path all the machine, and however in case of induction machine, flux is distributed approximately sinusoidal and the MF varies typically similarly. So in stator and rotor teeth, the flux density distribution is approximately as a sine wave with the superimposed third harmonics, as actual flux density distribution is the flat top as shown in the figure. We already discussed it first and third harmonics here. So we can say B60 is BG60 at 60-degree angle, which is a good estimate for that. It comes root 3 by 2 B average. That's come to be BM1. That is typically the value of peak flux density. So coming to calculation of MF for different parts, of MF for air gap we already discussed. So induction machine, the air gap is not regular and smooth due to geometry of the slot and stator and rotor slot, and it may lead to many physical phenomena such as locking, clogging, nagging, and presence of slot harmonics in that gap. The equivalent air gap is considered in the calculation, which we already discussed earlier. The flux density at 60 degree from the BG60 B average sin 60 and BG60 is root 3 by 2 BM1. For BM1 sinusoidal twisted, we can call it BM1 is pi by 2 into B average, and that is pi by 2 into 5 upon A, that becomes 1.36 B average. So we can call it ampere turns for air gap will be ATG, that is ATG into 800,000 BG 60 into kg/LG, where kg is a Carter coefficient, varies between Carter construction coefficient, which is varies between 1 to 1.1. So this final to MF for air gap, we can see where the Kc into Lg is equivalent gap length G dash, because that's also affected by presence of the typically of the slotting and ducts. The effect of slotting slightly increase the air gap. So new air gap idealized using the Carter coefficient, that means Kg varies from 1 to 1.1. As you can see how the slotting affects this. So from this we are able to get, typically we already discussed the MF required for the air gap earlier also. So now coming to the typically MF for stator teeth, two type of teeth are generally considered for design. And parallel sided sheet, the flux density is uniform throughout the height of the teeth, and the tapered slot, the width flux density is calculated at the height of 1/3 of the stator tooth height, as you can see in the both typically kind of slot. So this MF considering a parallel slot and tapered slot, the mean value of the ampere turns per meter can be calculated at the flux density at a section of 1/3 height of the teeth height from the narrow end, as method we have already talked about. So let the W at 1/3 be the width of the stator teeth at 1/3 height of the from narrow end. The width of the teeth is WTS 1/3, that is equal to pi in bracket D plus 2 DSS by 3, that is S divided by SS. So area of the teeth per pole at 1/3 height is ATS equal to SS on P to WTS 1/3 into Li. Now coming to MF for stator teeth. So let the WTS 1/3 be the width of the stator teeth at 1/3 height from the narrow end, and width of the stator teeth equal to WTS by 1/3, that's a pi in bracket D plus 2 DSS by 3 divided by SS, and area of the slot teeth per pole is at 1/3 height is ATS equal to SS upon P WTS by 3 Li, and BTS 1/3 phi m, flux density 1/3 height phi m SS upon P root TS Li. So now where you can call it like a typically BTS 60 is 1.36 BTS by 3. So flux density is calculated to get ampere turns from the magnetization characteristic. So total ampere turns comes 80 SM into DSS into 10 power minus 3 ATM. The DSS is already since it is in millimeter, that's why we have to take 10 power minus 3 to convert into meters. So this is the total MF required for the stator teeth. So similarly you can find out the MF for rotor teeth. So considering the parallel slot and tapered slot, the mean value of ampere turns can be calculated from the flux density section 1/3 height of the teeth from narrow end, and let the WTR to be width of the rotor teeth in 1/3 height. So we can find out the width of the rotor at 1/3 height, WTR 1/3, that is in pi in bracket TR minus 4 DR SR by 3 divided by SR in minus WSR, and area of the rotor teeth per pole at 1/3 height ATR equal to SR upon P to WTR by 1/3 and Li. So then that typically similarly as we find out for stator teeth, we can find out the total MF required for rotor teeth. For stator core, MF is in the stator core can be calculated from the flux density in the core. So thus the area of core equal to ACS into DCS Li, and the flux density is BCS m upon ACS. So to the corresponding value of typically transform the magnetization characteristic, find out Ln. So where the length of magnetic path is 1/3 upon pole P, that's 1/3 into pi into D plus 2 DSS plus DCS by P. So I'm required for the stator core is HCS is equal to LCS into ATM, which we got corresponding to BSS from magnetization characteristic of the material which we are using for this stator core. Similarly, we can get an MF for rotor core to calculate from flux density. So this area of the rotor core is ACR into DCR into Li, and flux density in the core is BCR equal to phi m on ACR. So corresponding value of the ampere turns per meter from magnetization characteristic ATM, and where the length of the core or let's say magnetic path in the rotor core is LCR equal to 1/3 of pole pitch, that is 1/3 in bracket pi d minus 2 DSR minus DCR by P, and the MF required for the rotor core is ATCR equal to LCR, this length of magnetic path, and the ATRM, that is the MF per unit length for the material which we are using from magnetization characteristic corresponding to the flux density of BCR. Then total magnetizing MF for typically for one pole can be AT60 equal to ATG plus ATS plus ATR plus ATCS plus ACR. It consists 5 parts, both the stator and rotor teeth, stator core, rotor core, and air gap. So magnetizing current can be calculated total MF by number of turns. Phi m equal to AT upon T as a basic formula. RMS value will be IM equal to AT into root into 2 into T, and from this you can typically find out IM equal to MF current per phase can be calculated as P into it is 80/20 divided by 2.7 kWs TPH sin 60, Kp 8 is 22.34 kTPH, and the peak MF related to magnetizing current is equal to 2.7 Im TPH kW divided by P ampere turn per pole. And then you can find out how the magnetic circuit calculation here typically for different parts. So we can say stator core, we already got it, area is Li into DCS, and length is at 1/3 of pole pitch, and the small AT from magnetization characteristic we have to find out, and the total AT is AT into L. Similarly for stator teeth, we got the area ASS P upon P into Li into W, and the length of magnetic circuit DSS, and then we got typically the AT from BH curve and got the total AT. Similarly for air gap length, the typically is area is pi dl upon P, and the length is kg into Lg, and we got the typically 800,000 Bg60, that's 8,000 Bg60 into Lg, the total MF, that is per unit MF, per unit length of MF. Rotor, similarly for rotor teeth, SR upon P into Li into WTR by 3, and the magnetic length in the rotor core is DCR, and the typically the per unit MF we calculate from get from BH curve, and we can calculate or multiply the length 8 into L. Similarly for rotor core, we can get a typically area is Li into DSR, and the length is 1/3 of pole pitch. So from which the of course per unit MF we get from BH curve, and then we can multiply this length which is given here to get the total MF. So this comes the total MF typically from the last column as a. So that's about the calculation of magnetizing current from this MF we already covered. So coming to the core loss calculation, the core loss is the state in the stator is only contributed to the stator teeth and core. So width of the teeth portion and the core portion are identified as width of stator teeth, WST equal to rho steel into volume of the teeth. So that is rho steel into DSS into ATS, and width of stator core is WSC, that is rho steel into volume of core. So rho steel into 0.25 pi in bracket DCS square minus DSS square into Li, and where P rho steel is equal to density of the steel. So now coming to core loss per kg for the maximum flux density for the stator core and stator teeth are identified by PLLC for stator core and PLST for typically the stator teeth. From this characteristic that is shown here for flux density, that core loss, and total iron loss in stator teeth we can say WST into PLST. That WST is the typically the weight of the teeth, total all the teeth, and iron loss is typically your stator core WSC PSC, and total core loss will be WSC into PLSC plus WST into PLST in watts. Like now the friction windage is also taken into as a no load losses, so they are accounted using empirical relation. So loss is depicted PFD. Friction windage loss consider PF equal to X percentage of output power, X divided by P upon 100. So that you can say for different power, how much is the percentage. So for lower rating, it's more higher percentage at 5.5%. When go to kilowatt around 150, it remains only 1% of the your output power. So that also we count in the no load power, no load losses. So we can call it core loss component of no load current can be IE equal to total iron loss upon 3V, 3 into voltage per phase voltage. So that becomes like WSC, PLSC, WLST, PLST plus PFO upon 3 into V. And no load current will be I0 equal to IM square plus IE square. And core loss resistance will be core loss upon 3V square. So that becomes WSC, PLSC, WST, PLST upon 3V square. And magnetizing current will be your V upon IM. And no load power factor will be your IL upon your I0 typically. So that's about the shunt branch parameters. We got it from this core loss and your magnetizing current. And coming to other equivalent circuit parameters, typically the stator and rotor resistances. So we get typically the resistance of the winding may be evaluated using a specific resistivity of the material length and cross section of the winding. And the stator winding resistance can be expressed as RS equal to rho LMT TPH divided by AZ. And you can find out how the length of magnetic current can be calculated from this kind of the terms like. So where the rho is the resistivity of the conductor, TPH is the stator turns per phase, LMTS is the length of mean turn of the stator in meter, and AH is the stator conductor area in meter square. So coming to typically that is for stator. Coming to wound rotor, the rotor winding resistance of slipping motor is given here RR equal to rho MT TR upon AR similar to like stator, and R dash referred to the primary, it will become KWSTS upon KWR into RR. That is we are referring from tons square, like we have to take this as a tons square, like kind of correct it up. So where the rho is the resistivity of conductor, TS and TR is the stator and rotor turns per phase, and LMT is the length of mean turn of the rotor in meter, AR is the rotor conductor area in millimeter square. So coming to typically rotor resistance for cage rotor, the rotor winding resistance of cage motor includes the resistance of all the bars and end ring. The resistance of each bar is RB equal to rho LB upon AB, and resistance of end ring is R equal to pi rho pi D upon AE into AE ohms, and the total resistance will be RR equal to SRRB RB into plus 2RE, because there are two end rings on both the sides. I'm considering all bar and two ends for finding out this resistance curve. So now coming to the total copper loss in bar, SR IB square and rho LB upon AB in watts, and total loss in two end rings, that is 2I square rho pi ds upon AE equal to 2 SR IB pi p square into rho pi d DE upon AZ, that is 2 upon pi into rho S R square LB square DE upon rho square P square into AZ. So total copper loss in the rotor will be SR IB square rho LB upon AB plus 2 upon pi rho SR square IB square D upon P square AZ equal to rho IB square SR square in bracket LB upon SR AB plus 2 upon pi D pi square A. So now coming to this rotor resistance must be referred from the stator to rotor to find out the total resistance of the motor V from the stator. Where let's consider MS and MR are the number of phases in stator rotor, TS and TR the number of turns of stator and rotor respectively, and KWS, KW are the winding factor for stator and rotor respectively. Total resistance of referred to the stator will be equal to MS TS into KWS divided by MR TR KWR square, effective number of turns of stator and rotor into rho into SR square in bracket I LB upon SR AB plus 2 pi upon pi D upon P square A in ohms. So coming to this resistance referred to stator, that will come MSTS KWS upon MRTR KW square into rho L SR square in bracket LB SRB AB plus 2 pi D upon P square A. For three phase machine, MS equal to 3 and MR equal to SR upon P and TR equal to P by 2 and KWR 1 for the cage rotor. The whole is a 1 bar, and the rotor resistance per phase referred to stator is RR dash equal to 4 MS square TS square equal to WS square upon rho upon MS, and in bracket LB SR AB 2 upon plus 2 upon pi D upon P square, and that becomes 12 for three phase machine 12 TS square PWS square rho in bracket LB SR AB plus 2 upon pi D upon P square A in bracket. So now coming to typically when the radial width of the end ring is large, as of 1, in a small induction motor, the end ring is multiplied by a constant K ring to take into account the effect of the non-uniform current distribution in the winding. So it becomes Rr equal to 12 TSC square KWSC square rho in bracket LB upon SR into AB and plus 2 upon pi D into P square into A into K ring, like as you can see in the typically small motor cage motor. So now coming to reactances, typically the leakage reactances. So leakage permeance of parallel sided slot. After considering the specific permeance of different flux path at different heights, the total specific permeance for parallel sided slot lambda will be equal to lambda 1 plus lambda 2 plus lambda 3 lambda 4, that is equal to mu 0 h1 upon 3 ws plus h2 upon ws and plus 2 h3 ws plus w0 plus h4 ws for given dimensions as shown in the figure, like in this parallel sided slot. Now coming to typically this leakage reactance for the total slot leakage is calculated both inster and rotor slot using specific slot permeance lambda SS and lambda SR. So slot rotor leakage is XS equal to 8 pi into Ft square TLR upon lambda SS upon QP, and rotor slot leakage is XSR equal to 8 pi Ft PH square LH lambda SR dash upon QPFS, and where lambda SR dash is equal to KWS upon KWR square SS upon SR into lambda SR. The rotor specific slot permeance referred to state. Now there are other reactances, leakage reactances. Zigzag reactance of stator and rotor is expressed as static reactance is XZ equal to pi by 6 xm upon m square in bracket 1 upon SS upon P square equal to 5 by 6 xm m square 1 upon QS square. Rotor leakage reactance in the same way XZR equal to 5 upon 6 xm upon m square into 1 upon SR by P square equal to 5 by 6 xm m square 1 upon Q R square. And total leakage reactance XZ will be 5 by 6 xm upon m square in bracket 1 upon QR plus 1 upon QS square. As you can see here how the leakage typically zigzag leakage flux really move in the from stator side and rotor side. So now coming to overhang leakage at the stator and rotor is typically depicted here, because in the overhang also there is a leakage flux. How to account for it as a leakage reactance? You can see the leakage flux out here. So the exact calculation of overhang leakage very difficult. So this is because of the overhang leakage reactance depends upon the length of overhang and its area, and leakage reactance also depends on the degree of saturation in ferromagnetic part. So once the empirical relation is equal to lambda 0 equal to mu 0 Ks Ts square upon L0 pi Ys, where L0 is the length of conductor in overhang and Ys is the slot pitch, tau is the pole pitch, and Ks is the slot leakage factor. So from the overhang leakage permeance, the overhang leakage reactance can be calculated as x0 equal to 8 pi Ft square L0 in bracket lambda 0 Qp, and that is equal to 8 pi Ft Ph square L0 in bracket 1 upon Q into mu 0 Kts square Ks square tau square L0 pi Ys and or equal to 8 pi Ft Ph square in bracket 1 upon Qp into mu 0 Ks square Th square upon Y pi S. Skew leakage reactance also expressed because there is a skewing in the slot, especially for the rotor. So SC skew is xm by 2 into pi tau upon SR in ohm. So the total phase leakage reactance of induction motor referred to stator is given xt equal to xls plus xlr, that is xss plus xr plus xgl s xzr plus x0 plus x skew. So lxx and xr the stator lot leakage reactance referred to stator. So we can call it XLS will be XSR plus XZS plus X0 plus XQ by 2, because that's we take half for stator and rotor. XLR equal to XSR plus XZR plus X0 plus XQ by 2 ohm. All are referred to the typically to the stator line. So total impedance per phase can be now calculated using the total resistance of the stator is RS ohm, and total leakage reactance referred to stator is typically XM, that is same as XT. X typically you can call it XT. Total impedance will be your ZS equal to under R square plus M square, where your short circuit current will be V IC equal to V upon ZS, and short circuit PF will be cos pi SC upon RS divided by ZS. The expression for the full load slip, once we got all equivalent circuit parameter, as follows, that FL will be minus B minus under root B square minus 4AC upon 2A, where A is equal to RS square plus in bracket XLS plus MX into XLR square plus 3V square by P0 into RR, where B is RR in bracket 3p square by p0 minus 2 mx into rs, where c is mx into rr square and mx is 1 upon 1 plus xlr upon divided by xm plus rr by rm. So now coming to the generated electromagnetic torque at any slip can be written as T equal to 3 upon S V square into RR upon S divided by RR plus RS plus RR squared by SC square total square plus XLR plus LX square. The total torque at full load can be obtained for substituting S equal to SFL. So at TR with 3 divided by omegas, that is V square into RR upon SFL, and in bracket RR plus RR dash upon SFL square plus in bracket LXLS plus XLR square. And starting torque can be obtained for putting S equal to 1. So that is ds equal to 3 upon S omega s equal into V square into RR divided by RR plus RS plus RR dash square plus XLS plus XLR square. So starting current IC can be written as ICST equal to V upon in bracket ZS plus ZR into Zm divided by ZS Rm plus Zm, and torque at full load can be obtained substituting S equal to SFL, that is ISFL. Torque starting current at full load can be obtained ISFL equal to V upon Z, and correct it. Okay, it's not torque, it's ZS in bracket as ZFL Zm into ZRFL plus Zm. So the full load efficiency of the induction motor can be written as the ratio of output to input power. The NFL को PO upon in bracket PO plus copper loss of stator, copper loss of rotor plus PFL friction index plus TSL into 100, where CU copper loss is 3 ISFL square upon RR, and CU copper loss of rotor is 3 RFL square RR, and TSL is WSC plus LSC plus WST plus LST, total iron loss in the machine, plus friction index, of course we have taken. Now coming to introduction to the thermal aspect of the machine. Now coming to as electrical machine is a complex 3D electromagnetic structure. It can be also classified as a complex spatial fluid dynamic structure with cooling medium and thermal rating of electrical machines. Typically safe limit of temperature rise on full load are one of the fundamental constraints in the design process. So temperature rise depends on the heat developed and the dissipation of the machine. So we can see that how the dissipation is by 3 methods we already talked about earlier, by the conduction, convection, and typically the mode of heat and then the radiation. So we call it mode of heat dissipation or conduction between the solid parts like copper, iron, and insulation, and convection is your solid to fluid heat transfer and to coolant or forced air, and radiation is from body to outside air. And as you can see how the sectional view for electrical machines for these all, I mean, as you see the radiation is outside, conduction is from one solid part to another, and how the convection heat is flowing in the total machine body. So now coming to typically why the heat is management is important. The temperature level impart directly on the lifetime of the machine, and high temperature increases the fatigue of a material, and basic rule of thumb is the lifetime divided by 2 for each 10 degree Celsius over the rated temperature, multiply the 2 for the each 10 degree below the. So heat management is important for reliable and robust machine, and you can see how the average affected typically life are with the temperature of the winding is shown as a characteristic, as empirical characteristic, and why how the winding you can call it hot spot are there with the temperature is quite high, as so see in the side graph how the temperature variation is there in the hot spot. So coming to like evaluation of thermal loading, so it's a heat transfer, we call it the input heat sources and cooling condition, and outcome is the temperature distribution, and the computational tool is analytical, empirical, numerical analysis, fundamental analysis, computational fluid dynamics, lumped circuit for heat transfer and fluid flow. And in order to determine the temperature distribution, a good estimate of losses has to be known, and the thermal characteristic and property has to be known. So coming to first approach as evaluation of thermal loading, so we can take thermal network as we already discussed about the thermal circuit for different sections of the motor. As you can see different parameters here, and or we can go for more accurate evaluation by using thermal finite element method analysis in thermal in 2D slot and thermal for 3D evaluation for the stator. Now typically another is a computational, how the computed fluid dynamic simulation gives the result. You can see the typically the 3D dimensions how the fluid analysis of coolant around the motor. Then coming to as a summary of the different technique, we can call it lump parameter thermal network, ideal for the early stage design of electrical machines and for optimization. Give a quick overview of the cooling in the machine. And thermal finite element analysis is ideal to detect hot spot and can simulate more complex geometry. And CFD, I mean, it does not no need of empirical data and very high computational time. So you can see how initially we take typically with the 0D with the lump parameter thermal approach, which is normally used for design optimization with, of course, with the empirical relation. Then for complexity we go to finite element analysis, or we go for CFD with typically with a high computational time, like with 2D and 3D. So now coming to temperature rise. So the surface temperature rise in induction machine is evaluated through empirical relation. The temperature rise equal to Cf into heat developed in watts divided by total effective cooling surface area in meter square. So Cf is the cooling coefficient and its value is calculated according to velocity of rotating body and the motor parts like surface of rotor, stator, stationary field coil, etc. So here you have this cooling coefficient in different parts and correspond to the typically in terms of velocity, where we the velocity here. So in cylindrical surface of stator rotor is given F equal to 0.03 to 0.05 divided by 1.5. So it's similar to iron, back of iron. Then it given cylindrical surface of DC armature, stationary coil, rotor field coil, ventilator, and commutator. So these are the empirical relation for after long calculations for this cooling coefficient of different parts of the rotating machine. Like, so now coming to typically a full load stator temperature rise. So heat developed in the stator is due to stator copper loss and the iron loss in the machine, and total effective area consists of stator outer and inner area and stator area of the two ends and ventilating duct. So we can call it total losses in the stator watts will be PSL equal to 5 into copper loss plus TSL, total typically the no load core losses. So that is equal to 5 into 3 SFL square into RS, and in bracket it becomes like a WSC into PLS plus WST PLST. That's a two part of the core losses for stator core and stator teeth. And stator outside cylindrical area is AS equal to 5D0 into LS TK, and the stator inside area is LASI equal to D into LOH, where LOH equal to LST plus 0.03 plus 2 in bracket LMTS minus 2 LST minus 0.14 divided by 4 square minus 5D divided by Q square and whole root of square root of that in meter. So cooling surface area of the two ends of ventilating duct ESD will be 5 upon 4 into D out square minus D square in bracket 2 upon plus and D meter square, and total effective cooling surface is ASS equal to ASI plus ASD, that is 1 plus 0.1 V plus ASO square, and peripheral speed V is pi d NHS in RPM, and final temperature rise is your CFS PSL total loss divided by ASS. So we can call it this full load. This is full load temperature rise of stator, and then coming to full load temperature rise of the rotor. So full rotor temperature rise can be found out in the same manner as for the stator. So in the rotor, the heat is developed due to the rotor copper loss only. The total effective cooling surface area in rotor consists of cylindrical rotor area and the side ending, as you can see in the diagram. So total loss in the rotor in watts will be PR, that is CPU loss, that is a 3I square FLRR, and surface area is AR equal to pi D0 in bracket L plus DR0 upon by 2 meter square, and total effective area is AR in bracket 1 plus 0.1 B bracket close meter square. The final temperature rise of the rotor is T rise rotor is CFL PRL upon AR in degree Celsius. So that is about the temperature rise of the rotor. Coming to harmonic torque. So harmonic fields are produced due to the various factors such as slotting, saturation, regularity in the air gap, and winding. The harmonic field produced due to the above factor get superimposed on the fundamental wave induced MF in the rotor winding and circulate current that are rich in harmonics, and these harmonics current interact with the harmonic field and produce the harmonic torque. And the net motor torque is the superimposition of fundamental and other harmonic torque produced in the machine. You can see the non-pulsating torque, and here non-pulsating typically really how it is really for the corresponding different speed and field, like those. Here the seventh harmonic torque also produced because of the presence of seventh harmonic in the flux wave, and that is forward, and for backward this is a fifth harmonic which is produced because of the pulsating field. That fifth harmonic torque is also produced here. Now coming to here, the Y harmonic induction torque is there, that we call torque speed in three-way induction, showing the effect of harmonic torque. So the winding harmonic produced because of three-phase winding carrying sinusoidal current given N equal to 6Q plus minus 1. The Q is the an integer, and plus for forward and minus for backward. So number of poles of the nth harmonics is n times, because it's a space harmonic, n times the number of the poles of the fundamental. So the synchronous speed of the nth harmonics is 1 upon n of the synchronous speed of the fundamental. As you can see, 4/5 harmonics is 1/5 of the synchronous, 7th harmonics is 1/6 of so well, these are affecting the typically called crawling and phenomena and slot harmonic. So if 7th harmonic produced is more pronounced, then it may prevent the motor speed exceeding about 1/7 of the normal speed at the downward slope of the resultant torque at this speed is stable running condition, hence the motor is said to crawl. This is normally happen when your voltage applied is low and low torque is reasonably larger. So another is the slotting harmonic. So slotting produces harmonics of order of n equal to n am plus minus 1, where a is the any number of integer number 0, 1, 2, 3, and m is the slot per pole per phase. So a motor with 24 slot, 4 pole has a 6 slot per pole and has a 2 slots per pole. So with m equal to 2, 11th and 13 harmonics are produced more strongly, where the 4th pole with 36 slot m equal to 3, so 17 and 19 harmonics are produced. So coming to here, a locking and cogging, we call it, if get typically locked at 0 speed, we call it cogging, and that happens if the condition, if you have selected the stator slot equal to rotor slot. So when the number of rotor and stator slots are equal, then the speed at all harmonics produced by stator slots coincide with that of rotor slot. So all the harmonics will try to exert synchronous torque at their corresponding synchronous speed, and machine may refuse to start. This is called cogging. So the harmonic reduction of harmonic torque. The harmonic torque produced in the induction machine can be reduced or eliminated by any one of the following methods. First method is chording. So harmonic induction torque is eliminated by reducing the stator winding harmonics. So for this purpose, chording winding with the integral number of slot per pole per phase is used. Integral slot winding, fractional slot winding are not used in the induction motor. Instead, they produce a asymmetric distribution of MM in air gap, leading to production of noise. So this is favorable slot per pole per pair, as in the table is given here for different slot combination. US upon P, that is typically stator slot, and number of poles are given here. So you can just, typically give the idea that how this will find out the different combination of poles and slot with the typically with the double layer winding. So coming to this reduction, the skewing also avoids if the stator and rotor or slots are skewed, the variation in flux density magnetic pole will be displaced in time phase along with the core law, resulting in the uniform torque, less noise, and better voltage found. So this skewing is only responsible for eliminating the slot harmonics, and which are responsible for cogging. So only skewing can avoid these like up. Now coming to some solved problems. So first solved problem, the stator of the machine have a smooth surface, but the rotor has open type of slot with slot width equal to WC slot width WT 12 mm, and length of air gap is L equal to, find the effective length of air gap if the Carter coefficient given below, no radial ducts are there. Carter coefficient is equal to 1 upon 1 plus 5 Lg upon Ws. So Carter coefficient comes from here, putting the value, it comes 0.54. So slot pitch Y is equal to Y plus WT 20 mm, 24 mm, and gap contraction factor for slot will be Ks equal to Ys upon Ys minus Kcs in Ws. Putting the value, it comes 1.37. Then this since there are no ducts, so gap contraction factor for ducts is Kg equal to 1. So gap contraction for slot Kg equal to Kgs equal to 1.37 into 1. That comes 1.37. So effective air gap length comes LGS equal to Kgs into Lg. That comes 1.37 into 2. That comes 2.74. So effective air gap length increases because of slotting. So coming to second, typically question of problem, estimate the effective air gap area per pole of a 10 pole slip ring induction motor with following data: stator bore diameter 0.65 millimeter, core length 0.25 millimeter, number of stator slots 90, stator slot opening 3 millimeter, and rotor slot 120, and rotor slot opening 3 mm, air gap length is 0.95 mm, Carter coefficient of ducts is 0.68, Carter coefficient for slots is 0.46, and number of ventilating threads each on rotor and stator, width of each ventilating is 10 millimeter. Now coming to the solution. So gap contraction factor for stator is Kgs equal to Y upon minus Kcs into W0. So putting the value, it comes 1.065, and the rotor diameter we can find out typically from that the diameter of air gap minus that TCH. So it comes 0.6481 meter, and the rotor slot pitch pi d upon slot number, so that comes 16.6797 millimeter, and gap contraction Kgs, putting the value, it comes 1.089. Now coming to the total gap contraction factor kg is equal to kgs kgsr, multiplying both the value, this comes 1.16, and gap contraction factor product comes kgd l upon l minus kcd ld wd. So putting value, it comes 1.089. The total gap contraction factor comes kg equal to kgs into kgd, that comes 1.26. The actual area of air gap per pole is ag pi d upon typically d into pi d, so it comes 51.05 into 10 power minus 3 meter square, and effective air gap area ag dash ag upon kg, so it comes 40 into typically 0.52 into 10 power minus 3 meter square. So now coming to problem 3, a 3-phase 50 Hz 6 pole induction motor has a 3 slot per pole per phase. So stator pole length is 0.2 centimeter, and there are 225 slots per 2 alternative sizes of the almost equal area are available for stator slot. So calculate the stator slot leakage per phase in each phase, and machine has a single layer winding. So you can see the dimensions here given for this slot. So for parallel slot, you can calculate specific permeance of the stator. So for you can find out for first slot, putting the value, it comes your permeance to 23.07 into 10 power minus 7 Weber per ampere, and stator slot leakage comes x is equal to, putting the value at pi f tph is parallel upon top lambda s upon pq, so putting it comes 0.978 ohm. Similarly, you can have a typically value, for deeper slot, so you put the value, it comes 1.296 ohm. So for deeper slots, it come typically, you can go higher than the previous value for second combination of the slot. So coming to, so that's to show the effect of how the slotting makes the effect in lift. Coming to fourth problem, 80 kilowatt for 40 50 Hz 3-phase 8-pole induction motor with slip-ring has a 65 stator slot and 5 conductor per slot. If the open circuit voltage measured across two slip-ring is not exceed 350 volt, find the suitable rotor winding, number of slots, number of conductor per slot, coil span, open circuit voltage between slip-rings, and approximate full load current per phase. Assume efficiency of 0.85 and power factor 0.8, and the closest even construction slot value. So coming to as a solution, number of slot per pole per phase of stator is m equal to typically 65 into 8 into 3.7, and let the rotor slot per pole q. The rotor slots will be multiple of ventricular slotting. The number of rotor pole number of stator slot a, and the to eliminate the harmonics SR S minus SR should not be equal to 0 or plus minus P. So all these avoiding the combination, we can say for SR here comes 50 and SS minus SR 65 minus 50. So you just get SR equal to 50, like 15. So now rotor induced voltage will be E2 equal to 3 by root 3. Rotor turns per phase here T2 upon E2 upon E1 into E1, and stator slot per phase, that is the number of stator slot into number of conductor per slot, 2 divided by 2 upon 3. So T1 comes 65 into 5 by 6. That comes around 54.10. So you can round up to 54, and turns comes, now from this relation it comes around 43 turns like. So now note total number of rotor conductors Z are equal to 6 into T2, that comes 258, and conductor per slot Z are R upon SR, that comes around 6, and coil for pitch winding, that's the number of slot, and 50 upon 8, that's 6.25. To have a coil pitch of 6, we need SR equal to 48. So SR 48 and SS minus SR equal to 65 minus 17. So coil pitch is 6 slot. So voltage between slip rings of open circuit root 3 into 2 equal to root 3 1 upon T1 into T2. Taking the value, it comes 350 volt. Now the full load current in rotor I2 equal to rotor MF upon T2. So with respect to motor rating, that's on efficiency 31 I1 cos phi 1. So 80 into 1000 by eta. So current in stator will be 8. Putting the value, it comes 154.38, and rotor MF is 85% of the stator MS. So putting this value, rotor current comes here 164.79 ampere. So coming to solved problem of 5, so a 75 kilowatt 3300 50 Hz 8-pole 3-phase induction star connected induction motor has a magnetizing current which is 35% of full load. Calculate the value of stator turns per phase if the MF required for 30-degree from pole position is 500. Assume kW equal to 0.5 and the full load efficiency and 0.94 and 0.86. So given that I have full load current, you can find out from kVA, it comes 16.23, and magnetizing current from here 35% of it comes 5.6805, and magnetizing from relation of magnetizing current, you can find out the stator turns per phase. So it comes around 318 turns like. Coming to sixth numerical problem, the magnetic circuit of 46 pole 3-phase star connected 50 Hz induction motor has the following parameter: pole length 0.15 meter, stator teeth 30 mm, rotor teeth 0.33 height from the narrow 7 mm, rotor teeth height 15 mm, rotor teeth 33 1/3 of height from narrow end 10.5 mm, stator board arm 0.4 meter, effective air gap length 0.9 millimeter, stator and rotor core depth 6.5 mm, mean 60-degree length of magnetic circuit at pole pair, stator core 0.25 mm, rotor core 0.16 mm, and the stator has a 70 slot with 8 conductor slot, rotor have a 49 slot and its setting factor is 0.9. So here is the magnetization characteristic is given for the material from which the stator core and rotor teeth and stator core teeth are given. So from this we can find out the stator slot per pole per phase, that comes to be putting value 4 and distribution factor for given phase spread and number of slots comes 0.958. Using full pitch winding, the stator winding factor is same as the distribution factor 0.958 and stator conductor 18 to 72, that comes now turns comes about typically 96 and stator voltage is 440 by root 354. So flux per pole is your 5P equal to voltage divided by 0.44 F into typically the number of turns into winding factor, it comes 12.44 into 10 power 3 Weber. And area of pole is AP equal to pi dl upon P, so it comes 0.0314 meter square, and average flux density per pole is B average equal to, giving this value, so it comes 0.395 Tesla, and BAG in air gap is 1.36 of this, so it comes 0.537 Tesla. MF for air gap is now 800,000 and 53 this flux density into contract 0.9 into 10 watt, it comes 387 ampere, and net iron length Ki into L, that becomes 135. The flux density in teeth of 1/3 height 5P upon SSP Li into W, so it comes 1.093 Tesla. So we see BTS 50 comes 0.48. So corresponding flux density, this flux density MF turn ATS is 1033. So MF required for stator, this turns into the length, that comes 30.99 ampere. Flux density in rotor teeth is calculated 1.07. So BTS is 1.455 2 into Tesla. So getting the MF per meter from material property ATR, it's 66.683. So MF required for teeth will be this into length of magnetic path in the this rotor teeth, some total MF required typically 13 ampere, and flux in stator core is calculated from half the net flux, that 12.4 into 10 power minus 3 by 2, that comes 6.2 into 10 power minus 3, and area of stator core DCS into Li, that comes about 8.77 into 10 power minus 3 meter square. So flux density in stator core, typically this flux in is a half 6.24 divided by this area, so it comes 0.707 Tesla. So same flux density obtained in rotor core. So for this flux density MF per meter is 108.77 for material property, and length of flux path in stator core is given 0.25 by 2, 0.125 meter, and length of path in rotor core is per pole is 0.16 by 2, that is 0.08. And for stator and rotor core, adding both to 108.77 in bracket the length 0.125 plus 0.048, that comes 22.229, and total MF BTS P60 comes 387 30.99 plus 13 plus 22.29, so it comes like 8064 to 53.28. So magnetizing current IM equal to 0.4278 rho 8060 kWh into TS. So value IM comes 12.627 ampere. So there are some more solved problem which you can do in the similar manner as we have talked about solved problem, with they are given with the answer. And any query, and thank you very much.